Lagrange Error Bound. Alright, Lagrange Error Bound. Now I'll be the first to admit that this looks pretty intimidating, but we're going to go through it one piece at a time. So suppose that we are using an nth degree Taylor polynomial centered at A to approximate f at some x value. Let that x value be bigger than A for now. If the n plus first derivative of f at x, the value we're trying to approximate the function at, is bounded on the interval from a to x, i.e., or in other words, if there is some positive number m such that the n plus first derivative at x can be trapped between negative m and m for all numbers between a and x, then the absolute value of r sub n of x has to be less than or equal to that m value that we trapped the n plus first derivative between over n plus 1 factorial times the quantity x minus a to the n plus 1, where r sub n is defined as the remainder, so that the original function f of x is the Taylor polynomial, the nth degree Taylor polynomial, plus the remainder. Okay, so what we're trying to do is we're trying to find how bad our Taylor polynomial was, so that when we tried to plug in some x value to the Taylor polynomial, how bad was that approximation from the actual function value. So in order to get that how bad it was value, I need to find the n plus first derivative, and I need to find a bound for it when I plug in that x value, so something that it's trapped between. And then I'm going to take that bound and plug it into this formula. So that bound is a number, so I'm going to plug in that number for m, and then I'm going to plug in my n, so n is the degree of the Taylor polynomial. I'm going to plug my n in right here and right here, and then I'm going to plug in my x and my a. So my a value was the center, and my x value is the number that I'm trying to approximate the function using the Taylor polynomial. So it looks intimidating, but we're just going to plug things in piece by piece. So the remainder, as in, that's how far off we are, right? So if you think about a remainder in division, it's like what's left over, so that is equivalent to the error, like how far off we are using the Taylor polynomial to approximate the function. So this is a formula that we need to keep in mind. But to use this formula, we need to find m, which is what the n plus first derivative at x is bound between. So let's take this formula and keep it written down and then go to the next example, or go to the first example. Alright, in this first example, for a particular function, it is known that f of 2 equals 8, f prime of 2 equals 5, and the second derivative for any x value, the absolute value of that, has to be less than or equal to 3 for all x values in the domain of f. Approximate f of 2.5 and estimate the error in the approximation. So to approximate f of 2.5, I'm going to need a Taylor polynomial. So the Taylor polynomial I'm going to use involves f of 2 and f prime of 2. So I'm only going to be able to find a first degree Taylor polynomial, or a linear approximation. So what I'm going to go ahead and do is set up my t sub 1 of x. So first is a Taylor polynomial, then I'll plug in 2.5. So the general formula says I need f of a plus f prime of a over 1 factorial times x minus a. So now I'm plugging everything in here. So my f of a is f of 2 plus f prime of 2 over 1 times x minus, my center is 2. So f of 2 is 8 plus f prime of 2 is 5 times x minus 2. So here's my Taylor polynomial, my first degree, first order Taylor polynomial. And I want to use that to approximate f of 2.5. So t sub 1 of x is exactly 8 plus 5 times x minus 2, but f is only approximately 8 plus 5 times x minus 2. So if I want to approximate f of 2.5, I'm going to plug 2.5 into this x. So f of 2.5 is 8 plus 5 times 2.5, whoops, 2.5 minus 2. So this is going to give me 8 plus 5 times a half. So this is 2.5 right here. So this is 8 plus 2.5, so this is 10.5. So that's my approximation, and I want to know how good or bad is my Taylor approximation. Alright, so I want to use my Lagrange Error Bound. So here's what I need. So I want the approximation, I want the remainder in using a first degree Taylor polynomial centered, or specifically at the x value of 2. So I'm going to write the general formula, which was r sub n of x is less than m over n plus 1 factorial times the absolute value of x minus a to the n plus 1. And now we're filling in all of our parts. So my n value is 1, because this was a t sub n Taylor polynomial, so n is 1, and my x value is 2.5. So the remainder, in plugging in 2.5, has to be bound by, so m. So let's think about m. Let's pull m off to the side for a second. So m was found by taking the n plus first derivative at x and trapping it between negative m and m. Well, the n plus first derivative, so if n was 1, then this is like I need the second derivative trapped between negative m and m. Well, that means that the absolute value of the second derivative has to be less than m. Well, I was given this piece of information here that said the second derivative at x is always less than 3. So my m value was given to me in this statement right here. So I'm going to plug 3 into my formula over n plus 1 factorial. So my n was 1, it's a degree 1 Taylor polynomial, so 1 plus 1 is 2 factorial times x minus a. So my x value was 2.5, my a value is 2, to the n plus 1. So 1 plus 1 gives me 2. So in other words, this is 3 over 2 times 1/2 squared. 1/2 is already positive, so this is 3 over 2 times 1 over 4, because I'm squaring the top and the bottom. So this is 3 over 8. So the error in my approximation, the remainder, in plugging in 2.5 into my Taylor polynomial, can be no greater than 3 over 8. So I was just plugging all my pieces into the formula. So I could only find a degree 1 Taylor polynomial because I was given f and f prime, and if I wanted to find the error, I needed the next piece of information and a bound on the next piece of information. So the bound, the second derivative, can be no bigger than 3 for any x value. So that's how I know I needed to stop at a Taylor polynomial of degree 1. So now let's try a different example. Alright, so here I want to use the third order Maclaurin polynomial for f of x equals sine x to approximate sine of 0.5. Alright, so here we know the Maclaurin polynomial. So sine x, so Maclaurin means centered at 0, is approximately x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on and so forth. So I want to use the third order. So in this case, because I have a third degree here, the third order is going to stop right here at x minus x cubed over 3 factorial. So I'm going to go ahead and plug 0.5 into that x. So sine of 0.5 is approximately 0.5 minus 0.5 cubed over 3 factorial is 6. So this is 1/2 minus 0.5 cubed. That's going to be 1/2 cubed, so that's going to be 1 over 8 over 6. So this is 1/2 plus 1 over 48. 1/2 is 24 over 48, so this is going to be 25 over 48. So that's my approximation for sine of a half, is 25 over 48. So how bad is this approximation? We want to use a Lagrange error bound. Alright, so we're going to need to plug stuff into r sub n of x is less than m over n plus 1 factorial times x minus a to the n plus 1. So let's plug in what we know. We know r sub, my n, is the the order, in this case it matches the degree, so this would be r sub 3 of x, my x is 0.5, so the remainder using a third degree polynomial at 0.5 has to be less than m, and I don't know what that is yet, I'm going to have to find it, so let's skip that, we don't know that. N plus 1, so that's 3 plus 1, so this is 4 factorial, times x minus a, so my x was 0.5, minus my center was 0, to the n plus 1, so that is going to be 4. So now it's all about finding this m value. So to find this m value, well, m has to be the n plus first derivative at x. I need to trap that. So I need to trap the n plus first derivative between negative m and positive m. Well, the n value was 3 here, so this is going to have to be the fourth derivative at 0.5. I need to trap the fourth derivative at 0.5 between two numbers, negative m and m. So I need the fourth derivative of f of x. So f of x was sine x, f prime of x is cosine x, f double prime of x is negative sine x, the third derivative at x is negative cosine x, and the fourth derivative of x gets me back to sine x. So in other words, I need to trap the fourth derivative at 0.5, so sine of 0.5 between two numbers. Well, the sine function is trapped between two numbers naturally. The range of the sine function is between negative 1 to 1. So let me make a little bit more space right here. So I can say that negative 1 is less than or equal to sine of 0.5 is less than or equal to 1. So that m value that I found then happens to be 1. So in other words, if I simplify this out, I have found a bounds on the error in this approximation. So 1 over 4 factorial is 24 times 0.5, so this is 1/2 to the fourth, so this is going to end up being 1 over 16. So whatever this quantity is, 1 over 24 times 1 over 16, 1 over 384 is the error in my approximation. So how far off was using my third degree Taylor polynomial? So my approximation was 25 over 48. It's not too far off. It's within 1 over 384. Alright, this last example is the trickiest. We're going to use the third order Maclaurin polynomial for f of x equals e to the x to approximate the square root of e. We're going to use the Lagrange Error Bound to estimate the error in the approximation, and then decide what degree polynomial is guaranteed to give an error less than 1,000th. Alright, so first we need the Maclaurin polynomial for f of x equals e to the x. So the center is 0. So the third order, I want t sub 3 of x at 0. So I'm going to need f of 0 plus f prime of 0 over 1 factorial times x to the 1, so x minus 0 to the 1, plus the second derivative at 0 over 2 factorial times x squared, plus the third derivative at 0 over 3 factorial times x cubed. And now I'm going to need to fill everything in. So the nice thing is that if f of x equals e to the x, then the first, second, third, fourth, fifth derivative are all e to the x. So e to the x is also f prime of x, which is also f double prime of x, and also f triple prime of x, and the fourth derivative at x as well. So here, if I want f of 0, that's e to the 0, so that's 1, plus f prime of 0, well, if e to the x is still f prime of x, then that's still going to be a 1, so 1 over 1 times x, plus f double prime of 0, since f double prime is e to the x, e to the 0 is still 1, so 1 over 2 factorial is 2, x squared, plus the third derivative at 0 will also be 1 over 6, x cubed. So let's write it a little nicer, 1 plus x plus 1/2 x squared plus 1 over 6 x cubed. So we did go through the process of writing it out, even though this is one of the ones that we should already know, because I want to point out that the derivative, just to remind ourselves, is e to the x over and over again for when we get to the Lagrange error bound. So if I want to approximate the square root of e, well, let's remember that the square root of e is e to the 1/2. So it's like I'm asking you to plug 1/2 into t sub 3 here. So t sub 3 of 1/2, it's going to be 1 plus a half times 1/2 squared plus 1/6 times 1/2 cubed. So let's go ahead and skip simplifying this out for a moment so that we can keep going in finding the Lagrange error bound. So for the Lagrange error bound, let's go ahead and start plugging things in as we know them. So r sub n, so n is the degree or the order, so r sub 3 of x was 1/2, has to be less than this m that I'm going to try to find over n plus 1 factorial. So n plus 1 is 4 factorial times the absolute value of x minus a. So 1/2 minus 0 to the n plus 1, so that would be 4 again. So now the trick here is finding m. So m has to be f to the n plus 1 derivative, so that's the fourth derivative, at 1/2. I need to trap the fourth derivative at 1/2 between m and negative m. So the fourth derivative is e to the x, so the fourth derivative at 1/2 is e to the 1/2. So I need to trap e to the 1/2 between negative m and m. The other way to think about this was I need the absolute value of e to the 1/2 to be less than some number m. Alright, so let me go ahead and clear out and make a little bit more space here. So instead of working with e to the 1/2, which was what I'm trying to approximate anyways, let's instead, if I can find a bound on something bigger than e to the 1/2, then that's definitely going to bound e to the 1/2. So e is about 2.71, so I know that e to the 1/2 is going to be less than 4 to the 1/2. So I know that e to the 1/2 is less than 4 to the 1/2. So I know that I can easily take 4 to the 1/2, that would be 2. So if e to the 1/2 is bound by 4 to the 1/2, then I know that e to the 1/2 has to be less than 2. So I'm going to go ahead and use 2 as my bound for m. So I'm going to go ahead and plug in 2 right here, and then we would simplify. So we get 2 over 16, and then 1/2 to the 4th would be 1 over 16. So here, this 16 would cancel with this 2, so this would be 1 over 128, which in decimal is 0.00781. So let's go back up to the question for a second because we're not done with it. We did find the Lagrange error bound to estimate the error in this approximation. So 1 over 128 is the error potentially in the approximation, or less than that, which is in decimal 0.00781. So what degree polynomial is guaranteed to give an error less than 0.001? So now I have to think about when I can potentially force this to be a smaller number. So the nice thing about this particular problem, I'm going to go ahead and change colors here, is that this m that we found is going to apply every single time because the derivative is the same for e to the x no matter what. So the only difference is that if I change the degree of the polynomial, this number here and this number here are the only things that are going to change. And this number here, of course. So if I use the 4th degree Taylor polynomial, that would make this a 4 and this number a 5 and this number a 5. So that would, of course, change the error in the Lagrange polynomial. So the 2 would stay the same because the 5th derivative at 1/2 would still be e to the 1/2. We'd still bound that by that number 2 that we decided on. So the 2 is going to stay the same. We're really just now trying to figure out how many times we have to up this number here. So this 3 to a 4 is going to change this to a 5 and this to a 5. We're going to have to see how far up we have to go in order to get this number here less than 0.001. So I'm going to go ahead and try to scroll down to make space for that. So here's what I need to calculate now, which is 2 over 5 factorial times 1/2 to the 5th. And we'll see what that quantity is. So this quantity in my calculator shows 5.208 times 10 to the negative 4. So if I move the decimal places 4 places to the left, I'm going to get 0.0004, oh, whoops, not 4, 5208. So this is definitely smaller than, going back up, 0.001. So I would need a fourth degree Taylor polynomial to get out an error that was less than 0.001. So all I had to do there on this particular example was increase this number and this number to correspond with the degree of the Taylor polynomial. In general, if I didn't have the e to the x function, the m would need to change every time as well. But it's just that in this case, the fifth derivative was also e to the x, so the bound happened to stay the same.